Hi group, it's Mrs. Schaus. I'm here today to go back and practice a little bit of working with radicals, and then also some of you mentioned needing to simplify radicals and work with rational exponents. And so I mentioned to some of you as we ended the previous week that this week I would go ahead and spend some additional time trying to, sort of bring you up to where we typically would have been had we ended our Algebra 2 year in a traditional fashion. All right, so first of all, in thinking about applications with radicals, some folks made comments to me like, I don't know how to get this formula. Well, in any of the applications that I'm going to give you here dealing with radicals, the formulas would be given to you. So you don't have to worry about how they're derived, you just have to worry about being able to use them. And I'm going to give you guys practice with a few different formulas, so this isn't the only one that you'll use. This is one that you have seen in an exercise that I assigned last week. Let's take a look. Officers use the formula below to determine the minimum speed of a car when the brakes are suddenly applied. In the formula, D here represents the distance of the skid that's left by the car, and F here is the coefficient of friction based on the road conditions. S, we had mentioned before, is this minimum speed. So we know what each of our variables represent. So if we are able to plug in any two of those three, we could solve for the other. So here in part A, find the minimum speed. So we're finding the S value. Given the frictional coefficient is 0.4, so we know what we're going to plug in there for F. And the skid distance is 58. Again, we'll just plug in 58 in place of D. So really, all we have to do here, after we plug in for each of those given items, is to let the calculator do the work here. We're not really simplifying the radical here like we will in some of our other problems. We're more using the radical in a real, in a real context to be able to, just kind of make sense of, in this case, of the minimum speed. I'm going to do the square root of the quantity 30 times 0.4 times 58 using my calculator, and it gives me 26 point, and then it goes on, 0.38181192, and so on. It makes sense for us to approximate that maybe out like to the nearest tenth. So I'm going to say 26.4 would be a good approximation of that minimum speed, and that is in miles per hour. And actually, now that I'm thinking about it, if it's the minimum speed that we're wanting to report out, probably they wouldn't round up. They would probably truncate. So I would prefer maybe to write this as a 0.3 or a 0.38. It's up to you kind of where you'd end that, but we probably should be rounding down or truncating. Okay? I certainly wouldn't mark it wrong if you put 26.4. That's a pretty decent response. Now in part B here, they want us to find the distance that the car will skid if the frictional coefficient is 0.8 and the car was traveling 70 miles per hour when the brakes were applied. In this scenario, we're finding the distance. So within the formula, it's this value for D that we're going to need to find. Still using that same formula, but plugging in two other or different unknowns to find, in this case, D or distance. The speed was 70. The value of F is 0.8. And it's this variable that I'm looking for. Now, this is just a radical equation. So in order to undo or get rid of this square root, I've got to square. I can't square this side unless I also square the other side. I want to keep balance. So now if I do 70 squared, that gives me 4,900 equals, again, this rooting and squaring undo one another, so I just get what's underneath the radical, 30 times 0.8 times D. 30 times 0.8 is 24. And so now if I just divide by 24 on each side, I get 204.16 repeating is the value of D. And that's in feet. Maybe I would just say approximately 204 feet. Okay, in addition to applications, we were going to work on some skills with radicals and rational powers. So these first couple of examples just ask you to switch between forms. I thought I would go ahead and put each of the different skills on here to make sure that we were feeling comfortable. So write the expression, I know it says each, I only gave one example here, in exponential form. To write it with a fractional or rational exponent, remember that we keep the base, and the power that we see here stays the numerator of the power once we switch to the exponential form. It is the index that sits here. Well, you might say, I don't see an index. Well, it's assumed to be a 2, a square root, or a second root, if you will, if we don't see a number there. That number becomes the denominator on the fraction. So the square root of b to the 5th power is equivalent to b to the 5/2 power. And similarly down here, they are giving us one that's already written with a rational exponent and asking us to put it in radical form. That means that I'll keep the base. The exponent that sits here, or the power, will be the same as the numerator of this power, but the denominator will tell us the index on the root. So this is the 4th root of the quantity 3x to the 7th power. You could also have written the 4th root of 3x, and that whole thing is raised to the 7th power. Whether we root and then power, or power and then root, doesn't really matter here. So either one of those would be fine and be equivalent and in radical form. Okay, now the directions ask us to do some simplifying. For all the rest of these problems, we're going to do some simplifying. First, dealing with rational exponents. So let's take a look at the directions. Simplify. Your answer should contain only positive exponents with no fractional exponents in the denominator. Okay, we know that when we simplify, we deal with negative exponents by taking the reciprocal of the base. So we definitely will want to have positive exponents only. We'll talk about this no fractional exponents in the denominator shortly. But let's begin just by sort of doing what we already know. And that is, inside this grouping, if everything inside here is going to be squared, then we want to, in fact, power each of these different factors. So I'm going to do a to the 4/3 squared. Well, that's a power to a power, which means we're going to keep the base, and when we're doing a power to a power, we multiply. To multiply, we get 8/3. I'm multiplying the tops and bottoms of the fractions together, essentially. I've got an a, which is really like an a to the 1st power being squared. That'll just give me an a squared. And then I've got a b squared squared. Again, keep the base and multiply the exponents. We're nearly done in this case, but we have a couple of factors with the same base. Since we're multiplying and we have the same base, we keep the base, and what do we do to the exponents? We add them up. Well, if this is in thirds, I would like this to be in thirds as well so that I can combine them. So I will change a squared to 6/3. And now to multiply, here I'll keep that base and add up 8/3 and 6 more thirds would give me a total of 14/3. So my final answer would be a to the 14/3, b to the 4th. Similarly here, I've got some powering to do for each of these factors inside this first parenthesis group. That means that I'm going to, when I do a power to a power, I'm going to multiply. So I will have u to the negative 2/4, but that is the same thing as a half, so I'll go ahead and reduce that down. V squared squared, again, power to a power, keep the v, the base, and multiply to get v to the 4th. And again, powering each of these means I'm going to have a u to the negative 3/4 and a v to the negative 1/2 power. The order in which I multiply doesn't matter, right? There's really multiplication here and multiplication here. So I would like to deal with these u's that are being multiplied together by keeping the base and adding up the powers. That means I will have, if I change this to, I'm guessing I'm going to go back to fourths here. This is negative 2/4 and negative 3/4. That would give me negative 5/4. And with the v, I would have v to the Oh, I could think of this in terms of halves as well. This is 8 halves minus 1 half. That would give me 7 halves. Now, those are combined quite nicely, or sort of simplified, but I still have to deal with this negative power. I'm kind of out of space, so let me make another column and kind of come up over here. If I take the reciprocal of the base, I would really have 1 over u to the positive 5/4 power times v to the 7 halves. Or maybe we would write that as v to the 7 halves over u to the 5/4 power. Now, I'm tempted to box that in and say, there's our answer, we're all done. But again, up top here, it not only said positive exponents were required, but no fractional exponents in the denominator. Why not? Well, because if I think of what this rational power really means, this could be rewritten as the 4th root of u to the 5th. And that leaves me with a radical in the denominator. And what we know is that we want our answers to be rationalized, right? We don't tend to keep radicals in denominators of fractions. So I need to multiply by a fancy form of 1 here. Remember, we talked in our Zoom session about the fancy form of 1 needing to be a power here, in this case it's on a u, that would give us something that's divisible by 4, since the 5 is already larger than the 4. So I'm actually going to make this a 3rd power, so that I've got u to the 5th times u to the 3rd. That would give me u to the 8th, and 8 is divisible by 4. What I do on the bottom, I've got to do on the top to create my fancy form of 1. It's supposed to be a 4. So up top, I would have v to the 7 halves times the 4th root of u cubed. And down below, I could think of this as the 4th root of u to the 8th, but the 4th root of u to the 8th is u squared. And so that might seem a little unusual to us, that we simplify and we've got some radicals in the numerator that involve u, but also some powers of u down below that do not have a fractional exponent. But the reason we want that is this whole rationalizing the denominator piece. Okay, let's continue on. A few more to look at. Notice in numbers 5 and 6, I've got a coefficient sitting out in front. That's just multiplication. So I'm going to bring that down, and I'm really just going to kind of ignore it. And I want to clean up this 4th root of 144xy squared. Well, I know if I can't really simplify a 4th root of just x to the 1st power, since the power is smaller than the root. And similarly here for y squared. Since this is smaller than a 4, I can't really do anything to simplify that either. But the number 144 can be broken down into 2 factors, one of which potentially is a perfect, in this case not square, but I can take a 4th root of it and get a whole number. So maybe I just want to start looking for what goes into 144 evenly that I suspect I could take the 4th root of to get that whole number. Sometimes these will usually be relatively small numbers, so you might do 2 raised to the 4th power. That's 16. Does 16 go into 144? Ah, yes, it does. It goes in there 9 times. And so I'm going to evaluate just that, which is a whole number when I take the 4th root of it. So 9 times 2 times the 4th root of 9xy squared. And I can go ahead and just do this multiplication, and I get 18 times the 4th root of 9xy squared as my final answer. Similarly, for number 6 here, the negative 10, again, just a constant that I'm multiplying by. I'd like to break that 324 down into the product of 2 numbers. Let's see. If you were to do 2 raised to the 4th power, again, you get that 16. 324 divided by 16 is 20.25. So that's not the one I'm looking for. Well, let's try 3 raised to the 4th power. That's 81. Does 81 go into 324 evenly? It does. In fact, 4 times. I'm just trying to walk you through how I'm choosing to break the number down into something that I can take a fourth root of and get a whole number. Okay? And then similarly for these variables, I'd like to break those down into products so that I can take fourth roots of things raised to, the fourth power, or at least a multiple of that fourth power in some situations. In this case, the m to the seventh is going to be rewritten as m to the fourth times another m to the third. And similarly for the n to the fifth rather, I'll write that as n to the fourth times another just n to the first power. I don't need to write the 1 there. And I'll evaluate all of those things that are going to give me nice values when I take the fourth root. So I've got negative 10 times the fourth root of 81 is 3. I can't take the fourth root of 4 and get a whole number, so that's going to stay in my radical in the end. The fourth root of m to the fourth is just m. I'll bypass this m to the third. The fourth root of n to the fourth is just n. And again, I can't do the fourth root of n to the first power. So now in the radical, in this fourth root symbol, I'll put all of those things that I didn't evaluate already. So that is the 4, the m to the third, and the n. And I do still have two sort of little pieces I need to take care of. One is that I need to do this multiplication to make it, as simple as simplify means as simple as possible. And I'll rewrite the rest. But then one last piece. We've talked about how when you take a root and this index is an even number, that we have to ensure that we have a positive expression here, okay? So we typically would just put absolute value signs around these variables if they are not raised to even powers. If they were squared, well, that would give us a positive anyway. So it's the case that we would need to put absolute value symbols there. Okay, and here right in the directions they said simplify, use absolute value signs when necessary. I'm not sure why it wasn't listed above. This is a pre-made worksheet from a program that I have, and I don't know why they didn't put the directions there. Maybe here they were just trying to give you a subtle reminder to check for that, or maybe not so subtle. All right, a couple more to look at. So I'm going to consider the fifth root of 160 uv to the ninth. Now, 160, can that be broken down? I'm looking again for a number that goes into 160 that I could take the fifth root of and get a whole number. So I'm going to look at what is 2 to the fifth power. That's 32. Does 32 go into 160? It does, in fact, 5 times. I'll leave the u to the first, but that v to the ninth I'm going to write as v to the fifth times v to the fourth. And we'll evaluate all of the roots that we can. The fifth root of 32 we just said was 2. I'm going to leave that fifth root of the number 5. I'll leave that in my part of my final answer under the radical in a moment. I can't do the fifth root of u and get that u out of the radical, so I'll leave it as well. The fifth root of v to the fifth is just v, since fifth rooting and fifth powering undo one another. And again, that stays under the radical. So I'll write times the fifth root of 5 u v to the fourth. I can still do the multiplication here. But I'm done. And I don't have to worry about absolute value here because this is an odd index. On to the last one, number 8. I'm going to see if I can rewrite 128. Again, that 2 raised to the fourth power is 16. 16 does go into 128 8 times. And I'd also like to rewrite the b as b to the fourth times b to the second power. All right, I'll evaluate what I can. So the fourth root of 16 is 2. I can't evaluate the fourth root of 8 and get a whole number, that is. Similarly, that a is going to stay underneath the radical. But the fourth root of b to the fourth does give me b. And again, this will stay in the radical as well since the 2 here is smaller than the 4. So I could say the answer is 7 times 2 times b times the fourth root of 8ab squared. I need to multiply. Since this is an even index, a fourth root, I want to put absolute value symbol here. And I'll tell you, I'm looking at an answer key off to the side here, but it says this is the final answer. And I think this is decent. This isn't a bad answer, but I have seen scenarios where they say if the power here and the root here can be written in a way that the fraction can be reduced, that you should reduce it. So if I reduce that power down to a 1/2 power, right, b to the 2/4 really equals b to the 1/2, I could write this as times the square root, not the fourth root, but the square root of b to the first, or just b. So this is a great answer. I would take that for full credit. This might be a little more cleaned up yet. So I'm hoping that just doing a little bit of extra work with simplifying radicals, dealing with rational exponents, and a little bit of the application will help you folks to feel better. I'm going to give an assignment today where you'll practice each of these skills, and of course, as always, get back with me if you have questions during our next Zoom class or Zoom office hours. Talk to you folks soon. Make it a great day.